Hi guys, I hope you guys are doing great and you had a nice weekend. So, welcome to the next lecture of operating system course. Before I actually dive into the content of today's lecture, I wanted to just quickly go through the course flow once again because I made a few changes to course flow because of our current situation of pandemic. So, this is how the course flow looks like now. It's more precise. So this course flow now contains the names of the assessments as well. For example, in week 4, which is the next week, you will have assignment 1, and then there is going to be another assignment in week 6, and so on. Also, there is a little bit change in the assessments because of again current situation of the pandemic. It's very difficult to have tests and quizzes, so I had to change the assessments to assignments and projects, and then final exam. Of course, you will get the date sheet about the final exam. But during the course, it's very difficult to have quizzes and tests and midterm. So I had the discussion with the colleagues and thought of changing the assessments to something like this. So you will have these assessments now. So there are 3 assignments, as I showed you over here, 3 assignments, and 30 marks, 30% of your total marks are for the assignments. Then there is a project. It's 30 marks, 30% of your total marks again, and we'll talk about projects and assignments in detail when I assign you those assessments. So project would be group project, and we'll talk about in more detail what this project would look like, what is the expectation of the project, and so on. But for now, these are the new assessments. I have already uploaded this file, this PDF of course flow on Blackboard as well, so please have a look at that. And this is the course flow we're gonna follow from now on. So just wanted to give you an update on the course flow, and I have updated the same thing in the syllabus as well. So you'll find an updated syllabus on Blackboard as well, so please have a look at the syllabus as well. So this is the course flow and this is what we're gonna follow. Let's now dive into our today's lecture, which will be on processes. Last time we discussed about operating system structures. We talked about different modes. We talked about how operating system is structured, what is the overall architecture of the operating system. Then we talked about kernel modules, and we created our kernel modules as well. We saw different commands in Linux, how to control your kernel modules, how you can modify a kernel module, how you can add a kernel module, how you can remove a kernel module from a kernel. So we saw this, so at least you got an idea of whatever we studied in the theoretical part. You were able to implement that in Linux during the practical exercise. So I hope you understand that. If you have any queries, if you have not understood anything regarding the theoretical part, any concept you were not able to grasp properly, or any command or anything that we did in the practical part, if you didn't understand that, please ask me. You can drop me an email, or you can check my virtual office hours. They are available now on the Blackboard. I have already made an announcement for that, so please check those virtual office hours, and you can join me in those virtual office hours, and we can discuss about any issues you are having. If you are not comfortable with the current virtual hours, office hours available for discussion, just drop me an email, and we can find out a way of meeting on Zoom or Blackboard outside those virtual office hours. So we can fix a meeting as well. So don't worry if you are not available during those virtual office hours. So just drop me an email and we'll talk more about it. Alright, so that's for this. Let's start with our today's lecture, and it's a very important lecture. It's about processes, and this is what we do every day when we are using our computer. We are just dealing with different processes. As a user, we don't know what operating system is doing in the background. As a user, we don't know what different applications or what different programs are doing in the background. We are just using them. But today you will get to know what are these processes, how operating system is handling these processes, how different applications or programs are dealing with the processes, and then later on in the second video, which I will create after this video, we will create some new processes, we will kill some processes, and we'll try to do few exercises on running some Linux programs on different processes, Linux commands on different processes, so that you get a feel of how these processes are actually controlled by the developer, by the programmer, so that we can develop our own programs and create our own processes and so on. So I will try to implement almost all these concepts in the exercise. Few of them might not be implemented, which I think if you know the theoretical part of that, that would be sufficient. But as long as you know how to create processes, how to manipulate different processes, how to create parent and child processes, how to manage them, if you know this part of this topic, I think that would be more than enough. So let's dive into processes. So first thing first, what a process is. It is very important to know, first of all, what is a process. I mean, why we call it a process, why we are not calling it a program, what is the difference between a process and a program. And you might have heard about threads. What is a thread? What is the difference between a thread and a process and a program? So we're not going to talk about threads today because we have a separate lecture, a whole lecture on threads, so we're going to talk about threads in that lecture. But today we are going to distinguish between a process and a program, which we are going to do now. So what is a process? Process is a running state of a program. So first of all, if we see what a program is any application, any software that you have installed on your operating system, or that comes bundled with your operating system package. For example, Notepad is a program, Microsoft Word is a program, Windows Media Player is a program, your browsers, Firefox, Chrome, they are all programs, right? So they are all programs. So how do you execute these programs? If you are using a graphical user interface, you will just use your mouse, double click the icon of that program, and it will launch, right? So this is what a program is. Now moving to the process again, as I said earlier, process is actually the running state of a program. So any program that is currently executing, currently running, is called a process. So as we discussed in our previous lectures as well, in order for a program to run, it has to be in the RAM. It has to be in the main memory. If a program is not in the main memory, processor cannot run it. Your CPU cannot run it. So in order for a program to run, it has to be in the RAM. It has to be in the main memory. So for example, I want to run Chrome browser. Right? I want to run a Chrome browser. What I'm going to do is I'll just double click the icon, Chrome's icon, and as soon as I double click the icon, a part of that program moves to the memory, to the main memory, where processor sees that program and launches that program and executes that program for you, and that starts appearing on your screen. So the part of the Google Chrome program, what a Google Chrome program actually is, or what any program is, it's just bunch of lines of codes, right? So if I'm talking about Chrome, there is some lines of codes written behind it. Similar, it's exactly similar what we do for our C++ or C program or Java program. There might be a main method that is running, it's calling some other function, it's performing some loops, it's working on some control statements like if and else. So these are some lines of codes that are written behind each and every program we see on our computer. So Chrome example, if we go back to it, it's something very similar. When I launch Chrome, for example, if I double click a Chrome icon, what it will do is, what your operating system will do is, it will take a part of your program, Google Chrome program, and put it inside your RAM. Processor will come and try to execute that program from the RAM. And this is what a process is. The part of a Google Chrome program inside the RAM is called a process. Very simple. Now the question arises, why the whole program is not loaded in the RAM? Because it's just one program, it should be whole loaded into the program. It doesn't work like this in operating system. Why it doesn't work like this? Because your programs might be very heavy. Let's talk about Microsoft Word for now, right? What Microsoft Word does is, it's a word processor. What it does is, it lets you write some reports, type some text on it. you can style it. Then it helps you in checking your grammar also, so there is a spell checker also running in there. Then if you're writing very complex reports, then it gives you an ability to add some bibliography as well, so there might be some extensions that you can use. Then there are some images that you can use in that. Then there is a printer. If you want to print a report, then you can do that as well. So Microsoft Word itself is a huge program that has, I think, millions of lines of code behind it, and the whole program is not required all the time. For example, if you don't have a printer attached to your Microsoft Word program, that printer part of the program is not required all the time, right? Similarly, if you don't want to add bibliography or references to your report, you don't need a bibliography part, right? So these are the things which are not required to be always running. So for RAM, since RAM is very limited, it's not like your hard drive which has terabytes of space. RAM is very limited, it has only few gigabytes these days. So we cannot load the whole program because it has to load other programs as well. Microsoft Word is not the only program that is running at one time for your computer. So there might be some other program. Operating system itself needs a lot of space for its programs also in the RAM. So what operating system does is, and this is how the programs are installed, and you will see that how you program your software, and how some of the main programs will be loaded and the rest of the portion will stay away from the RAM unless and until they are required. For example, if I want to print Microsoft Word, inside Microsoft Word, that code of printing will be brought into that section of the code of printing will be brought into the RAM, and then it will be executed. Otherwise it will not be executed. So this is the whole concept behind a process. So a part of a program that is inside a RAM is called a process. Very simple. So process and program, some people say process and program are same thing. As long as they are talking about general overview of the process or a program, yes, we can call a process or program, but technically they are not same. There is just a thin line between them. A program is just a collection of code that is not active all the time. That is a passive part of a program. But a process has to be active. Process has to be in the memory. If the process is not in the memory, then it means that it's not a process. So in order for the process to be a process, it has to be in the RAM. So a small portion of the whole software or a whole program that is in the RAM is called a process. I hope it is clear now. Now, just like any other program, process needs to run in a sequential manner. So it means that it has to run line by line. So first line will be executed first, then second line, then third line, and so on. So just like your any other program written in any programming language, it will start from somewhere, then it will go to the next statement, then next statement, and next statement, and so on. This is how your program runs, and this is exactly how your process is going to run, because process is just a part of your program. So if we talk about process in a little bit more detail, process has many parts. It has many parts. So a process has a program part, obviously the instructions part or the statement part that contains the statement for the process. Then it has information about the registers. So sometimes your programs might need to write something on the register, so it has the information about which registers we are using and how many registers we are using. Then it contains some space. We normally call it a stack, where it stores some temporary data, just like any temp folder in your operating system. It has a stack where it contains temporary data. Then it definitely contains some other things like local variables, like memory addresses, then function parameters, and so on. So this is also a part of a process. And then it has a data section for global variables. So we all know what a global variable is. So in order to store global variable, process keeps them in the data section also. And then it also contains, besides many other things, it also contains information about the memory, right? About the memory heap. Heap is just a part of a memory that is used for running the process, right? So these are some of the many parts of a process, and program obviously has these parts and many others, right? So these are just few of the processes parts. There are other parts of the process also. We'll talk about them in coming slides. And if we talk about the program, which is just the bigger part of the process, contains many other things which are not only the process, right? So these are some of the parts of the process. Now As I said earlier, it's the same thing, that a program is a passive entity stored on the hard drive. Can be an executable file or many other files required by that executable itself. And a process is an active part. What active and passive means: a process is in the RAM and program is not always in the RAM, right? So this is the difference between a process and a program. And as I said, in order to load a program, it has to be in the in the memory or the RAM. So if it's not in the RAM, it cannot run. And of course, one program can have multiple processes, right? So if you go to your task manager also, you can see that some of the applications, they have many processes. So if you see on my Firefox, these are the current running applications on my system. So if I see Firefox, it has 3 different processes inside, right? So maybe I have 3 different tabs open. That's why these are 3 different processes. So these are the things. I mean, you can see that how different processes are running on your system. So for example, PowerPoint is running, and it has, if you can see that over here, that it has the actual PowerPoint, and then it has a printer driver installed also, so a separate process is running for that as well. So this is how you can see the processes. And there are some background processes, of course, that are running as well, which are not present on your GUI, on your graphical user interface, but they are running in the background. For example, your calculator is running, maybe your antivirus is maybe running in the background, the service is running in the background, your mic services are running, camera services are running, so many other things. So these are all the processes that are running in the background, right? So this is how it looks like in Windows. Now this is what I told you, that process, this is a process, and these are different components of the some of the many components of the process, but these are the major ones. Some of the others are just part of these components. So this is the memory address starting from 0, and the maximum memory address, maximum size of the process, sorry. And then it has a stack for containing temporary variables. Then it has a heap. This heap and stack can grow and shrink based on what we place in them. Then we have data for storing variables and so on. Then the instructions and the text. So this is how a process looks like. Now I hope it is clear what a process is, what is the difference between a process and a program, what are different components of a process. We'll talk about different parts of a process once again when we talk about process control block. But for now, this is just a brief introduction of a process. Now what we're gonna do is we're gonna talk about why process is so important and what are different states or types. I would not call it types, they are normally in technical language called states, right? So what are different states of a process? So it's very important that we see what different states of a process is, states of the process are. So these are few of the states of the processes. So there is a new state, there is a running state, there is a waiting state, ready state, and a terminated state. So let's talk about them one by one. So what is a new state? As the name says, whenever a process is created, it is in its new state, right? So as soon as a process is created, it's called to be in its new state, right? Because process has just been created. Now running state, the other stage is the running state. Running state, as the name depicts, that whenever the process is being executed, whenever the process is running, whenever the instructions of this particular process are running, obviously it has to be in the RAM, only then it is called a process. When the process is being executed by the processor, we call the process to be in the running state. So it has to be in the RAM and it has to be allocated the processor, only then it's called a running process. Then the other state is called a waiting state. In a waiting state, a process will be in a waiting state if a process is waiting for some IO devices or some other events to occur. For example, I mean, you want to print something in Microsoft Word, but printer is busy, so the process of printing of Microsoft Word will be in the waiting state, right? Because the IO device itself is busy, right? So that's why the process in such a cases will be in the waiting state. Then there is a ready state. Ready state comes after normally the new state, and obviously I will show you a chart now where you will see that how ready state and running and waiting state can be hopped by the process in between. So what a ready state does is, Whenever a process is ready and it's waiting for the processor to come and execute it, it's called to be in a ready state. So for example, a process is in the RAM and it's waiting for the process to be allocated to it. And who will allocate a processor to a process? Operating system, right? And a part of operating system that allocates the processor to a process is called a scheduler, and we'll talk about that in a while as well. So a process is said to be in a ready state if process is waiting for a processor. So very simple. And finally we have the last stage, which is the terminated stage, and as the name says, as soon as the process has completed its execution, it is said to be in the terminated state, or we call it that process has been terminated. So these are the 5 stages that are very important for the life cycle of a process. And let's see this in a little bit more detail through this example, and how these different states work when a process comes. So as soon as a process comes, what happens is we see operating system sees that there is a new process available, right? So a process comes and it has been created, so it's said that this process is in the new stage, right? Now once the process is created, it's created to do something, right? If a process is created and it will not do anything, then that process is useless and it should not be created, right? So any process that is created, it has to do something. Now that process can be checking emails, it can be sending prints to your printer, it can be checking running as an antivirus, checking for viruses, it can be your sound processor, it can be your image processor, it can be showing something on the screen, it can be any process, right? So as soon as the process is created, it becomes ready. What does mean ready? That processor has everything it requires, right? So the processor has been loaded into the memory, right? This is what it requires to run, right? So process is now ready and it's waiting in the RAM, in the main memory, for the operating system to allocate a processor to this process, right? So a CPU will come and run this process, right? And what does it mean, running the process? Run its instructions, run the code written inside this process, right? So it's in the ready state now. It has been created, now it's in the ready state, and as soon as operating system sees that the processor is free now, it will allocate the processor to this process, right? And as soon as this process has the processor allocated to it, it moves from ready to running state. So whenever operating system gives a processor to a processor will start executing it, will start running that process, and the process will move to the running stage. Very simple. That process started, it was in the ready state, processor has been allocated to the process, and processor started executing that process, and this process is now in the running state or executing stage. As soon as the execution is done, the process is terminated, it's completed. Very simple. So this is the simple flow of a process. However, the processes are not always very simple like this, that they will come, they become ready, they run, and they terminate. This is the ideal scenario, and if something like this is happening, then excellent. This is the type of processes we need. But normally this is not how operating system works. This is now not how processes work. What happens normally is, if a process is in a running state, so a processor is working on the instructions on this process, and the process is said to be in the running state. At this time, operating system finds another process that is of highest priority or higher priority than this process. What operating system will do is, operating system will take the processor from this process, snatch the processor from this process, and give the processor to the other processor, or to the other process that has higher priority than this process, right? Once again, so CPU or your processor is running the instructions or code of this process. So this process is said to be in the running state. At this time, operating system sees that another process comes that is of higher priority than this process. What operating system will do is, operating system will take this processor from this process and give the processor to the other process that has the higher priority than this process, right? So when the processor is given to the other process, this process is no longer in the running state because processor is not executing the commands in this process anymore. So this process will now go back to its ready state, right? To its ready state. And this type of movement, this type of move is normally called as interrupt. The process running or process execution has been interrupted by the operating system, and the processor has been given to some other process. So it's no longer in the running stage anymore, it's no longer in the execution state anymore, so it moves to the ready state, right? So it's back to the ready state. So this is another thing that can happen. So we already discussed one of the route, that new process came, it came to the ready state, it moved to the running state, and then it terminated. Now the second thing that can happen to a process is it was created, got to the ready stage, then moved to the running stage, but then some other higher priority process came, and this process has to move back to the ready state. This is another thing that can happen to a process during the execution. Now let's assume the same thing. So we have discussed the two stages. Let's talk about the third case that can happen. So let's assume that this process is running. So processor is executing the code inside the file of this process. Now, for example, line number 5 has been executed. Line number 6 came and it said that this line said that I need to print, right? So this is for asking for the printer for an IO device, right? Now processor or operating system in general has to execute this this statement. What operating system will do now is, well, processor will tell operating system that this guy is looking for an IO device or a printer in this case. So what operating system will do now is, operating system will take the processor from this guy and give it to some other processes that are waiting, right? And this process will be moved to a waiting stage, right? Why it's moved to a waiting stage? It is waiting for an IO device to occur, IO event to occur, right? Or any other event to occur, right? Now that waiting stage might be ignorable. For example, printer was available, so from this waiting stage the process straight away moved, printed something and then moved to the ready state. Or this waiting can be long, because printer was busy, it has to print 5 other tasks before it can print this process. So it might have to wait in this waiting stage for long. So this is what operating system has done wisely, that while this process is waiting or while this process is looking for IO, the processor should not wait. Processor should be processing something else. Because if processor keeps on waiting for the completion of this process, the other processes will keep on waiting and our system will be very, very slow. And this is the whole thing behind an operating system, that it schedules the processor in such a way that all the processes they get a chance to be executed, and we'll talk about that in a while. So this is the other stage. So as soon as the print is done from the waiting stage, this process will again move to the ready state, and as soon as the processor is available, this will move to the running state, and when everything is done, this will terminate. So this is how 3 different scenarios can change the overall states of a process. This is how the life cycle of a process looks like. I hope it is clear, and I think these are the only 3 stages that a process state would ever come across. And this is just a general view. Of course, within a process of a process execution, these stages can occur many times. So if the process is in running stage looking for an IO device, it will finish that IO device process, that goes to ready state, then again come to running state, then again in the code, if somewhere it's looking for some other IO device, it will again go to the waiting state. So these stages might occur many times. Obviously new will not occur again and again, but the rest of the stages except new and terminated can occur again and again. So that's why you see a cycle over here, repetition over here of these stages. So this is how a process states works, process states work, and this is how whole life cycle of a process during the execution looks like. Let's now talk a little bit about PCB, we call it, process control block. What this is this is the whole life cycle of a process. So a process in itself contains some information. That information can be about itself, that can be about many other things, and we'll see what this information looks like. So a process is associated with some information, and that information is normally stored in a process control block. So we have a process A. Process A will have these things associated with it. I mean, these are few of the many things that are associated with process A. So each process, if there are 1,000 processes in an operating system, there will be 1,000 process control blocks, right? So each process will have this process control block that will contain some information. Sometimes this process control block is also called a task control block. So let's see some of the major things this PCB contains. So first thing is the process state. So this process control block will contain the state of a process, right? So we just discussed the states of a process. So whatever is the current state of the process, it will be stored in the process control block. Why this is important? Because if you see, for example, over here, so the process was in the running stage and there was some high priority process that comes, and operating system had to give processor to this new process. This process has to move to ready state now. It was interrupted. So it was maybe at his 5th line or 6th line of execution. When it comes back, it has to move from 5th or 6th line. It should not start running from beginning. So the state of the process, where it was, what it was doing, what was the current line number or whatever, it has to be saved somewhere. We'll talk about this in a little bit more detail when we talk about context switching. But for now, this is the concept that whenever a process is moved from its running state to somewhere else, the state of the process should be saved somewhere. It's just like an example of you're playing a game and you are done for the day. You have played the game for 6 hours or so, and now you want to save the game and want to play again tomorrow. So you just want to save your game, come back tomorrow and start playing the game from where you saved it, right? So you restore from there. You will not start playing game from the first stage. So this is exactly the similar theory behind it, that the save of the state of the process should be saved, and where it is saved, it's saved in the process control block. This is where it's saved. Next thing is the program counter. Program counter is basic. Before we get to program counter, let's talk about process number also. So each process in operating system will have a unique number, which is called a process ID or a process number. So if there are 2 or 3 processes, operating system should be able to distinguish between them. Operating system should know which is process number 1, process number 2 and 3. So they should have unique numbers behind, just like your student IDs. So each student has a different ID, right? So that's why each process in operating system should have different process IDs. So process number, which is over here, is the process ID of a process. Then we talk about the program counter. Program counter just tells us that what exactly is the next instruction, right? So we need to know, as I just told you, in the execution of the process, we need to know how many statements have been executed, how many are remaining. So 5 have been executed, next statement is the 6th statement. So this is exactly what is stored over here in the program counter, that what is the next statement, what is the next instruction to be executed, that is stored in program counter. Then we have some registers. As I said, that sometimes your processes might need to store information in the registers. That can be for any reason. For example, there is a special process that needs to run very fast, so instead of saving the information in the RAM or in the cache, we need to save this information somewhere in the registers, because the registers are extremely fast. If you remember in the last lecture, last lecture, we talked about the hierarchy of memories. So how registers are very fast, then cache comes, and then RAM comes, and so on. So sometimes you need to store some of the information that can be very rapidly accessed when required. So this type of information is normally stored in registers. So if something is stored in the registers, for example, if some of the process information is stored in the register, then process control block should know what are those registers where this information is stored. Then memory limits, obviously, I mean memory management, you need to know how much memory is allocated for this process, what is the address space, where exactly in the RAM this process is saved. So everything about the memory is stored in the memory limits. Then we have list of open files. Obviously, I mean how many files, I mean your process does not need to be only one program, it might need other files, right? It might need some other programs to be run, it might need some other text files to save data or read data. So this is the list of open files, how many files this process has opened, right? Why you need to know this? Because sometimes, for example, this process terminated without any reason. For example, your computer was stuck, your memory went full, so some of the processes your operating system has to remove from the memory, and your process was unfortunately the one which was removed from the RAM. Then at least the process control block information should be there to close those open files as well. Although it doesn't work like this, just wanted to give you some information of why we need to keep a track of open files as well. Then there is some other information like CPU scheduling info. So I mean it's about scheduling, and we'll talk about scheduling and queuing in a while, and we'll talk about some algorithms of queuing and scheduling and priorities. So it tells about the priorities. For example, if this process is of high importance or high priority, that information will be stored in process control block as well. So whenever operating system sees that flag, it will just take out the processor from other processes and give the processor to this process. And then there is some accounting information like CPU usage, how much CPU it has used, for how long this process has been running, and stuff like that. So this is the process control block that is storing some important information about your processes. Now obviously your operating system might be running thousands of processes at one time. When I'm saying one time, we as humans, we don't see, but they are not running concurrently at the same time. It depends upon how many processors you have. So I'm going to talk about that in a while, but this is how your process control block looks like, and this is how the information is stored in a process control block of a process. Now let's talk a little bit about process scheduling. As I said earlier, that it is very important for the operating system to manage the processor wisely, because if it's not managed wisely, some of the processes will keep on waiting, right? So for example, let me just quickly draw something for you, just for you to see that how it looks like. So what I'm gonna do is I'm gonna draw a processor here. So this is a processor. I'm gonna call it processor, and then we have a process here. Let me make it black, right? So let's call it P1. So what I'm going to do is, in order to run this process, this processor should be allocated to this process P1, right? So operating system should allocate the processor to this process, and this processor will start executing the lines of codes inside this process, and once it's done, it will be terminated, right? So this is the whole scenario. Now let's assume another process comes. Let's call this process P2. Now this processor is currently working with P1. Let's assume that it's working with P1, and another process P2 comes. It's very confusing between process and processor. That's why I keep on having this confusion. Anyways, so if this new process P2 comes, now since P1 is already being executed by the processor, and obviously this whole thing is being managed by the operating system, so operating system is taking care of this whole scenario. So what's happening over here is that since operating system knows that what is going on, and this is the boundary is operating system. So operating system knows what is going on. Operating system has information about new processes coming. It has information of which process is being executed by the processor. It has information of every other thing, memory and so on. So if the operating system keeps on waiting for process 1 to be completed before the processor is allocated to P2, then this process 2 might keep on waiting forever, because maybe process 1 is very long and it will take some time for process 1 to complete its execution, and P2 will keep on waiting. So this process, for example, is Microsoft Word. This process is, for example, your browser. Let's assume that you want to do something, you want to get some information from Google to complete your report over here. So you want to run these processes at the same time, which we are doing in modern operating system these days. So we can open multiple processes, multiple programs, and we can run them at the same time. But how is it happening? This is what I want to tell you right now. So first thing is that operating system will make sure that not only one process is taking the processor. It will keep on switching this processor between different processes. And how it does that, how it gives priority to this and then give priority to this is what is called the scheduling algorithm, and we'll talk about them. But in your modern operating systems, what happens is your system does not have only one processor. So it will have multiple processors, right? So it might have 4 processors. It might have 4 processors over here. So at least 4 processes can run at a time. So you can see like this. So each processor can work on one of the processes, and everything will work smooth because each processor can run one process at a time. So it might be running this, and these 2 are run by other processor. So if you have 4 processors in your computer and you have 4 processes, then it's very simple that each processor can run one of the processes, and it's absolutely fine. Operating system has no hard time scheduling the processes. But this is not what is happening all the time. So for your computer also, at a time you might be running 10 different applications, 10 different programs, and these are not the only applications that are running. The operating system has its own processes that are running in the background as well, right? So as I showed you earlier in the task manager, if you see, there are a lot of processes, that are 83 processes that are running in the background, and there are only 7 applications that are running in the foreground. So in total there are 90 processes, at least 90 processes, assuming that these are only having one process at a time. At least 90 applications are running at this time. So we cannot have 90 processors installed on your computer, right? So we have normally 2 processors, 4 processors, and we'll talk about how these four or 2 processors are then switched between here and there, so that at least as a user I don't see any delay in my commands. So this is what the main responsibility of operating system is, to manage your processes. So operating system will manage these processors in such a way it's switching between these processes and these processors in milli and nanoseconds, that we as users, we don't feel any lag, right? We don't feel anything that it's taking some time. It's not taking time. We think that our computer is doing this very fast. It's performing all the commands we need very quickly. So this is just a background of what is going on, just to give you a brief idea of what a processor is, how a processor processes a process, and how operating system is supervising the whole scenario. So this is what is meant by process scheduling over here. So if there was only one processor, then only one process can run at a time. But operating system is so wise that it switches between different processes so quickly that we don't know that there is a lag, right? And this is what I said, that if one of the process is taking forever with the processor, then the other processor will keep on waiting, and keeping other processes wait is not a good idea. So this is what operating system does. So better the process management, better the performance of the machine. We know this, right? So this is called the process scheduling, and this process scheduling is done by operating system using many things, many things, right? So some of those things is that operating system maintains some of the queues, right? So it maintains a job queue, it maintains a ready queue as well, it maintains a device queue as well, and this is how they look like. So operating system maintains few queues. So if some processes are already working with CPU or some other devices, rest of the processes that are looking for CPU or other devices, they will stay in the queue. So for example, let's have a look at this diagram. It's a queuing diagram for process scheduling. So we have a processor. We're assuming we have only one processor with our system, and there is a process. Let's assume currently there is no process in the ready queue, so a process comes and it will go to the ready queue. So any process that is ready for execution will go to the ready queue, right? So all the processes that are ready for execution, that are in the ready state, if you remember over here, any process that is in the ready state will go to the ready queue, right? If there is nothing in the ready queue, that first process will go and CPU will, and your processor will start executing that process. If 5 processes are already in the queue and 6 process is already being executed by the CPU, another process that comes will have to wait in the ready queue, right? Assuming that it's already ready for the execution, so it has to wait in the ready queue. So there is a ready queue being maintained by the operating system that is keeping track of all the processes that are ready for execution, and this is how operating system knows that what other processes are waiting. So if one of the process, for example P1, is done execution, it will pick, operating system will pick now from this queue another process, and the processor will start executing. And which process it will come, it can be first come first basis, it can be shortest time, and we'll talk about these algorithm, how operating system picks from this queue the processes for execution, right? So this is one of the queues, the ready queue, which is the list of all the all the processes that are ready for execution. Then there is another IO request queue. There is another queue called IO queue. So what happens is CPU is processing one of the process, and then that process needs a printer. So operating system will take the process from that processor from that process and put that process in the IO queue, right? Just like what operating system did for the processes that were in the ready stage. So any process that wants an IO will be put in IO queue, right? So why it's put in the IO queue? Because those IO devices which the processes are looking for might be already busy doing something else. For example, printer, there are 5 other jobs that printer is doing right now, so that's why this process which just came will be put in the queue, and then from this queue operating system will provide, based on what hardware is looking, what IO devices that these processes are looking for, they are moved to those IO devices. And similarly there are some other things, but I'm not going into the detail of these things, but these are the 2 important queues that are being maintained. And one other queue which is not available in the diagram but it's available over here is the job queue. The list of all the processes in the system, all the processes, every process that is available in the system will be in the job queue. So operating system keeps a track of all the processes in the job queue. Now those can be waiting, those can be running, so many, I mean all the processes that are in the system, any state they are in, they will be in the job queue, except if they are in the ready state, they will be moved from job queue to the ready queue. So this is the important thing to note over here. And as I told you earlier, that operating system is the one that makes sure that processes get enough chance to be executed by the processor, and how operating system schedules which process is going to be the next for execution. This part of the operating system that schedules these processes is called a scheduler, and the algorithm that is being used by the operating system to schedule these processes for execution is called a scheduling algorithm. And we'll talk about all these algorithms in coming lectures, but for now these are just simple concepts, simple definitions of what a scheduler is. Scheduler is just a part of operating system that schedules the execution of the processes, and the algorithm that is used for scheduling is called a scheduling algorithm, and there are many scheduling algorithms, right? So this is called a process scheduling. And now when we are talking about schedulers, there are in general 2 main schedulers in operating systems. One is called a short-term scheduler, and we call it a CPU scheduler as well. It is used for executing, right? It is used for executing. So which process will be executed? Obviously this schedule is a part of operating system, right? So overall what this is being done is done by operating system, but operating system has different components that are given different tasks to perform certain things, right? And scheduler is one of them. So what CPU scheduler does is, or it's also called a short-term scheduler, what it does is it will keep track of which process to be executed next. So which process will be executed next, this track will be kept by CPU scheduler or short-term scheduler, right? And this CPU scheduler is referred many times, frequently, obviously, because it has to make sure that it switches between different processes so quickly that whole operating system works efficiently, performs efficiently, and the system, I mean the computer itself, is performing well, so the user doesn't see that there is a lag. So this CPU scheduler will take care of all the processes that are to be executed next, right? And who will execute them? CPU, the processor. And this is very fast. Normally this scheduling is very fast because it is done in milliseconds, and it has to be done in milliseconds because scheduler is switching between different processes very quickly. Then there is another scheduler which is called a long-term scheduler or a job scheduler. What this does is this will select the processes that will be brought from the job queue to the ready queue, right? The processes that are ready now, they should be moved in the ready queue, so that from ready queue the short-term scheduler will take care of the ones that are going to be executed next. And from the job queue who are brought to the ready queue, long-term scheduler takes care of that. Obviously, I mean, it will take some seconds or minutes, which is just fine because ready queue is normally always full. Not always full, I mean, it has already many of the processes in the queue so that the processor can execute them. So even if this long-term schedule takes some time, some seconds, it's absolutely fine because ready queue already has some processes inside it that still need to be executed. So even if some process comes, it's going to be at the back of the queue. And so this is called a long-term scheduler. So two schedulers: short-term scheduler, which has to be very fast because it's talking about who is going to be the next process to be executed, and then long-term scheduler that will bring processes from the jobs queue to the ready queue, and it can take some time. Then there are two types of processes, and just wanted to give you some information about this because I'm not going to go into a lot of detail of what IO bound process is and what a CPU bound process is, but you should know what these processes are. So let's talk about IO bound process. What an IO bound process is, this is a process that takes more time doing IO operations, right? So a process that is printing maybe 100 pages again and again, it needs different hardware again and again. So for example, one of the processes just reading the file from the hard drive or writing to the files on the hard drive, because it's just constantly interacting with the hardware. So these type of processes that take more time, that spend more time on doing IO operations and less time doing CPU operations, are called IO bound processes. IO bound processes. And in contrast, the processes that take more time, that spend more time doing CPU bursts, working on CPU, that require CPU for long. For example, these are the processes that are doing computations or mathematics or I mean doing complex expressions. So they require computation from CPU. They don't want to print something, they don't want to save anything to the hard drive. So they are using IO less and they are using CPU more and more. So these type of processes are called CPU bound processes, right? And long-term scheduler normally uses mix of them. So this is the only information I want you to know about IO bound processes and CPU bound processes. We are not going into more detail of these processes right now. So we have been talking about traditional operating systems up till now. What we're going to do now is we'll dive quickly into mobile operating systems as well and see how they are different from our traditional desktop operating systems. Now, the problem with mobile devices is they have limited resources. For example, the screen size, the screen cannot handle multiple interfaces at the same time. So if one application is running, the application is in the background, right? So this is one of the biggest limitation of your smart devices. So your screen real estate is extremely important. Only one interface can remain there and rest of the things have to go in the background. But for your traditional operating system, you can share your screen doing different things. So rest of the things are in the taskbar, and some of the things can be on the foreground, and you can simultaneously work on multiple programs. even when they are on the foreground as well. For example, let's take an example of iOS as a limitation of mobile systems. There is only a single foreground process. It's maintained by the interface, so rest of the things, they have to be in the background. So there can be multiple background processes running, which is absolutely fine, but on the foreground there can be only one process, one processor or program in general. So the processes that are running in the background, they are still using the memory, they still might be in the running state, no problem, but they are not displayed, which is absolutely fine as far as our mobile devices are concerned. But some of the, these are the limitations. Now what it does is, if we give a quick overview of why this is happening, and I mean why iOS is designed like this, is because of other limitations as well, not only the screen size, but the memory is limited, processors are limited, then hardware is limited, other hardware devices are limited, printer and so on are not there. So that's why what iOS does is it limits the programs or processes to single process only, and those are for short tasks only. So I mean, by short tasks I mean they are not running there for days. I mean, even if you are having a phone call which is 1 hour or 2 hours, it's still a short time comparing to other programs that are running on your desktop system. That I mean, my system remains open forever. I mean, some of the applications are always running on my system, and the other background things that are running are applications that are only getting notifications. And if you have a background music running as well, it's also running in the background. So in the front ground, it doesn't have to be in the foreground or the front ground, right? Android does something very similar, but there are less limits. What Android does is, instead of running the processes, it runs the services. Services are lightweight processes, and we'll talk about services when we go to maybe chapter number 7 or 8. But for now, you can think of services as lightweight processes. They don't take too much space in the memory, and they don't have an interface as well. They don't require an interface as well. So in Android, what it does is it runs a lot of services in the background, and those services are just fine running in the background because they don't need interface anyways. So they don't have to be in the foreground anyways, and they need less amount of memory space. So this is some of the limitations of mobile devices, mobile operating systems. And this is the only thing we're going to talk about mobile devices for now. When we talk about I think security, we come back to mobile systems again, if I remember correctly. But for now, mobile systems, this is what we're going to talk about, mobile system, as long as process management is concerned. Let's now talk about context switching, which I was mentioning a couple of slides ago. What happens in context switching is, as I mentioned earlier when I was showing you this diagram, that operating system has to quickly switch between different processes. Let me go back to a single processor again. So operating system has one processor, and it has two processes running. Now what operating system has to do is, it has to quickly switch processor between these two processes, so that both processes keep on running and they don't keep on waiting for each other for very long. So when operating system switches this processor from, for example, P1 to P2, there is certain time that it takes from switching, right? So currently, for example, processor is running process 1. Now for example, process 1 now needs an IO device, and operating system knows that P1 now is looking for an IO device. So operating system will switch processor from P1 to P2 now. Now this switching of processor from P1 to P2 is called a context switch. When you are switching between processes, an operating system is handling this, it's called a context switching. Now there are some more details to context switching. When you are moving from when you are context switching, it is very, very important, as I said earlier, that you save the state of this process. It's very important to do that. And when the processor comes back, it has to restore that save state. So this is also part of context switching. So overall, the context switching is switching between different switching processor between different processes. But when you are switching, you have to, you means operating system has to make sure that the state of this process is saved as well. and when the context switch again happens, when from P2 the processor moves back to P1 again, operating system needs to provide information to the processor that it has to execute this process P1 from the same place where it has stopped execution. So this whole concept is called a context switching. One is the processing, switching between the processes, and the second thing is saving the state of a process and then restoring the state of the process from where it stopped. This whole concept is called a context switching, and this is what this slide is all about. So it has to save the state of that, but as I said that saving the state, restoring the state takes time. It will not take one hour or 2 hour or 1 second or 2 seconds. It is happening in a milliseconds, but it also depends upon the process structure as well, right? So if the memory, for example, if you remember that we discussed about sorry, we are here. So if you remember, we discussed about this one. So it contains all the information. Now operating system has to go back and check the registers. It has to go back and see which state it was in. It has to check the open files and so on. It has to check many things. So what is happening is basically a lot of time is being spent in context switching, right? So when this is happening, when switching is happening, for example, we assume that there are only two processes. When switching is happening, processor is not doing anything, right? Processor is just switching from here to here. That's it. Processor is not processing anything. It's just switching. So if this switching, for example, if processor again came back to P1 and it has to restore, and operating system has to restore its previous state, then operating system is still, let's assume operating system is still restoring the previous state of process 1, and processor is still just waiting for the operating system to give process 1 to allocate processor to process 1, because operating system is still busy restoring the state of the process. So by that time processor is just waiting. So all the time of the processor is wasted, right? So there is an overhead, there is a cost of time, there is a cost of effort. I can give you an analogy of this as, for example, you are alone at home and you are playing your game, and suddenly there is a bell rings at the door. What you have to do is, since you are home alone, you have to go to the door to see who is there. So you were already doing a process, which was, you are already playing a game, which is P1, but then suddenly there was a doorbell, which is P2. So what you have to do is you have to stop your game, you have to stop process 1. So what you're going to do is, maybe you're going to save your game over here, and then you have to go to the door to see who is out there. Then once you are done with the door, you will come back to process 1 and you have to restore from where you have saved your game, right? So this is exactly what is happening over here. The processor which is you have to switch between different tasks, different processes, and operating system is the one who is, in this analogy nobody is looking at you, but operating system is supervising everything. But what if somebody on the door was there and he was a naughty kid, he just rang your bell and ran away? So all your effort of going to the door, all your effort starting from saving the process, saving your game, then getting up, going to the door, coming back, this all is an overhead, right? It's an overhead. It's the time you spend, it's the effort you spend. But if process 2 was of no use, then the whole time was wasted. As I said, that waste is a cost that includes time, that includes effort, that includes resources as well, so many different things, right? So this context switching, as you switched from process 1 to process 2, similarly as this processor moved from process 1 to process 2, then from process 2 to process 1 again, it has a cost behind it. It has a cost, or we normally call it overhead behind it. It has an overhead behind it, and this overhead is very, very important. We cannot keep our processor free all the time. We have to make sure that our processor is busy doing something. We cannot keep our processor free or idle at all. This is the last thing which we as an operating system need, right? So we cannot do that. We have to make sure that our processor is always engaged, it's not sitting idle. So that's why we use context switching, and this is the whole concept of context switching. I hope this is very clear. Up till now, if you don't, even after the lecture, if you don't know anything, if you don't understand any concept, just drop me an email and I will definitely get back to you. So the next concept we're going to talk about now is the process operation. We have been talking about what a process is. We know different components of a process. We have gone through different process states as well. So we have an idea of what a process state is, what different process states are. We now know the context switching. We now know that context switching has an overhead behind it. So we know all these things. But we need to know that how a process is started and how we can kill it, how we can terminate a process. If we don't know these two stages, then the rest of the things we have studied in between, they are of no use, right? That's why I have also created some exercises which we're going to do after this theoretical part, where we create processes, where we terminate processes. I don't remember terminating a process. We'll see if we get some time terminating the process, but at least we create a process, we'll manage a process, and so on. So that's why I have created some exercises on that. So if you understand how to create a process, why we are creating a process, then you are good to go with this lecture. So two major operations that we do normally on processes is process creation and process termination. And this is just a normal tree, process tree, that looks like this in Linux. Just I wanted to show you over here how a process can have child processes as well. So for example, whenever Linux operating system starts, init process is started, and it's given an ID 1. I'm just saying this is just an example. So and then a user logs in, so and then kernel starts some threads as well, then your secure shell is started as well. So this init process is the parent process that triggers, that initiates some new processes, right? So this is a parent process and it has some child processes, in this case login, kthread, and sshd. So these are the child processes. Now in a process tree, whenever we are creating processes in operating system, child processes can have more children, right? So they can have further children, just like what is happening over here. So as soon as a user logged in, it logged in into bash, the user logged in into bash, and then from bash user ran a command ps for seeing the processes, and user also ran a command for emacs to run an editor. So now from this process it has two children over here. One is ps for processes and one is emac, and for this process it's a parent process to this bash process, which is a child to the init process. So this is the tree. It's a hierarchy. A process can be a parent, a process can be a child as well. A process can be a parent and a child at the same time as well. So this is the hierarchy, how it looks like for the processes in Linux. Now in order to create processes, what do we do and what information do we need to create a process? Before we do that, let's talk about, as I said, that what a parent and a child process is. Whenever a process is created, it's a parent process, unless and until some other process created it, right? Just like what happened over here. If it was init, it has no parent because it was initiated by Linux system itself, and then it initiated some other process. So first of all, a parent process is a process that has some children, right? So if init was the only process, we'll not call it a parent process, right? Because it is the only process. And if, for example, we'll not call pd flush a parent process because it doesn't have any children. So it's important to know that not all the processes are parent, not all the processes are children, right? So but some processes are parent, some processes are child as well, child processes as well. So processes can be parent, processes can be children as well, and child processes can have other children as well. So not necessarily a child process is only a child process. It can be a parent process as well. Now, as I mentioned earlier as well, that each process will have an ID. We normally call it a process identifier or process ID. PID is the abbreviation for that. And when we are talking about a parent and child processes, how the resources are being shared. For example, we have a parent process, Microsoft Word. It has a child process, print, for example, because it wants to print some documents. How this parent process and the child process, they share resources. Resources can be memory, it can be IO resources as well, it can be processor is a resource as well, so it can be processor as well. So how they share these resources? So they can share resources in these forms. Parent and children processes, they can share all the resources. They can share the resources. So any resources, if parent has 5 resources, all the children can share these resources as well. That is absolutely fine. So one way of sharing the resources is this way. The other way of resource sharing between parent and children processes are child processes can share some of the resources of parent processes, right? So for example, a parent has 5 resources, child processes can only share 2 of the processes, so they can share just a subset of the parent resources. So this can be another case. Then another case can be parent and child process, they don't share any resources. A parent has 5 resources, but it doesn't want to share those resources with child because child might not need that, right? So for example, Microsoft Word, if you take an example of Microsoft Word again, Microsoft Word is a parent process and it has a child process, spell checker. So parent process doesn't want to share printer as a resource with this child process because child process doesn't need that, right? So sometimes parents, they know what children are looking for, so they share those resources, and sometimes they don't want to share those resources because they are not required by the child processes. Then we have execution options as well. Parent and child processes, they can run concurrently, they can run as processes, so both of these can run as well. So processor, so there are 2 processes, for example, so there is another process as well. So this is a child process P2, this is being handled by processor 1, and this is by being handled by processor 2, so they can run concurrently as well at the same time. So this can happen as well. So this is one of the execution option. The other one is parent waits until the child terminates. So parent is not executing, it's just waiting for the child to do something and then parent will execute. For example, again Microsoft Word example, or what we can do, I'll give you another example. For example, torrent example, not a good example, don't do that if it's illegal, but this is the example that comes to my mind now. So some of the torrent software, torrent hosts, torrent software, what they do is, if you put the download, they will give you an option that whenever the download is completed, the software will close itself, right? So the software itself is a parent process, and the download, whatever download is happening, is a child process, and parent will not do anything, it will just wait for the child process to complete. So parent, the whole software, will just wait for the download to complete, and as soon as the download is completed, both parent and child process, they both will be terminated. So this is what uTorrent does if you have selected that option, for example, that as soon as the download is completed, the software will close. So this is just one of the examples of the execution options of parent and child. So one more important thing to note over here, we have talked about 2 different things over here. So resource sharing is one of them, then execution options was another one. Then another thing is address space. So address space is how the memory is being used by parent and child. Main memory is being used by parent and the child processes. So child processes can duplicate parent, so they can use the same address space. I mean, they can use the same space as the parent is using. So parent has given some of the space to the child and child is executing in that space. That can happen as well. Or a child can have a different program loaded to it. So a child might load another program, for example, browser, your Google Chrome, it's a parent, and it has a child process of one of the tabs open, and in that tab you want to open a PDF. So you click on a PDF link, and then that program, Acrobat Reader or whatever PDF program you have, it will be loaded. So a child process will load another program. So when another program is loaded, that program is not loaded in the space of child, it will be loaded separately because it's a separate program in the RAM. So address space can be managed like this as well. Then in Unix, this is what we're gonna do today. We're gonna use fork command, system call, to create a new process. This is how it works, fork command. So when we call fork, uh, it will start having two branches. One of the branch is the parent branch, right? And it will have a child branch. So we are creating one child, and there is one parent. So parent will not do anything, it will just keep on waiting. In this example, obviously parent can do something if required, but in this case what is happening is, as soon as a fork command is executed, and I will go into a lot of detail of fork command and how to use that when we write our program later in the lecture. So what happens in Unix is, whenever we call a fork command, a fork system call, uh, it starts two branches. One is the parent branch, and it starts a new branch called a child branch, and child process will do something. In this case it's just executing something, and then child program exits, and then it will merge with the parent, because whatever child was created for, it has done that, and now it has merged into parent, and parent was just waiting for the child to complete something, and then parent will resume or terminate, it depends, right? So this is how fork commands work in Unix, and I'm not going into the detail of fork command right now, because we will spend a lot of time working on fork command in the exercises. And this is how our program looks like. We're going to write something like this, maybe not exactly this, but something like this. So in order to in order to create a command, create a process, we use a fork command, and we're going to talk about what these flags are, why we use these if statements and so on, why we use these libraries. But just wanted to give you an idea that this is how a program for creating a process looks like. But we are going to write our own program. So we have talked about process creation. Let's talk a little bit about process termination. So just like process creation, program needs to terminate. Process cannot keep on hanging forever. It needs to terminate somewhere. So in order to terminate a process, normally exits system call is used, just like fork command we used. So exit is the command that is used for terminating a process. Now when the process is terminated, it might merge into parent, and when it merges into parent, all the resources that were given to the child process will be deallocated by the operating system, right? And this is how it should happen. If child is done with the process, all the resources, for example IO resource or memory space that was given to the child process, should be taken by the operating system and should be used somewhere else. It should happen like this. So on process termination, sometimes a child will merge into parent, and then operating system will deallocate all the resources. And sometimes some other things will happen. This is what happens when everything is normal. But sometimes parent wants to terminate a child process, right? Parent wants to terminate a child process. The child process has not completed the execution, but in the middle parent wants to terminate the child process, and that can be done using an abort system call. But what would be the reason? Why would parent want to terminate a child process? There can be several reasons. One of the reason was the child has exceeded the allocated resources. So the memory or the memory space given by the parent to the child process, it has exceeded that space. So and parent cannot afford giving more space to the child, so it will just terminate that child process. This is one of the reasons. Second reason would be that the task given to the child, it's not required anymore. For example, print again. So we wanted to print something, but now we think that print is not required, so we just cancel the print on the dialog box, and hence this child process will be aborted or terminated. And the other thing is and this is normally handled by the operating system as well, but currently it is being handled by the parent. So parent thinks that parent needs to exit now, and it needs to kill all of its child processes. So some operating system, they don't allow child processes to remain there if parents have terminated already. They want parents to terminate all their children so that system remains clean. So another reason would be that parent is now terminating, parent is exiting now, so it wants to terminate all its child processes. So this can be another reason why parent would want to terminate the execution of a child process. So these can be few of the reasons. Then sometimes operating system also handles termination of the processes, which is very normal. So operating system can terminate processes, that is absolutely sure, because of many reasons. One of the reasons can be these reasons can be these ones. For example, the resources allocated are more resources are being asked by the process. Task given to that process was not there anymore, and an operating system doesn't have more resources, right? So there can be many reasons. So what operating system does is, when operating system terminates, it normally does cascading termination, which means that it will kill all the child processes, all the grandchild processes of the parent process. So if a process has children and grandchildren, it will operating system will terminate all of them, right, if required. The other thing is the sometimes what happens is, and this is a little bit confusing sometimes, but I will try to explain in a simpler way. So what happens is, what is a zombie? Sometimes it is asked in the exam. I will not ask this, but yes, you should know what is a zombie process and what is an orphan process. So a zombie process is a process if the parent has not called a wait command and the process is still there, right, and the child process is still there again. And now in order for the parent process to make sure that the child process has completed its execution, because it's normally responsibility of the parent process to terminate all the child processes, and if parent process is waiting for the child process, is allowing the child process to complete its execution and then terminate, the parent normally calls a wait system call. This is what I showed you. The parent will call a wait call, system call, and it will wait for the child process to complete its execution, and then it will terminate the child process, or child process will terminate automatically. So if parent has not called a wait call, not executed the wait system call, then the process will become a zombie process. It will become a zombie process because parents are still busy doing something else, and it has not waited for the process, and this process is now zombie. Nobody is there to take care of it. But normally all the processes in the operating system, all the child processes in the operating system, they become zombie for a while, right? Because not necessarily parent will wait for their termination. Parent might start doing something else over here, and this child process will execute over here, for example, will complete its execution over here, but parent is still doing something else. So this will become zombie for a while. But when parent is done doing something, it will come back and see if the children has completed the process or not. Child process has terminated, has completed its execution or not. And when it sees that it has completed its execution way back, it will just terminate that. But yes, this child will become a zombie for a while because parent was doing something else and parent didn't see that child for a while. So yes, most of the time, or at least in most of the cases, parents are not waiting for the child processes to execute, and they are not doing anything. Normally all the processes are doing something. For example, you sent a print command on word processor, and in the meanwhile you will keep on working on something else. You will format your document or so on. So this normally doesn't happen, but in some cases, yes, it does happen that a parent is waiting for the child process before it starts doing something else. So this is how a process becomes a zombie. And on the other hand, if a parent is terminated without invoking wait and without killing a child process, it becomes an orphan. So the parent has terminated and it has not killed its child process, and it has not called a wait command as well, because parent maybe forgot. Parent was terminated because of something else. Parent was frozen, so operating system killed it, but the child process was not killed, so it becomes an orphan, right? So there was no parent for that, and it got unlinked from its parent because of some reason. But obviously operating system will take care of it. Operating system will close all of them because operating system is doing periodic checks on all of them. So if there is an orphan, it will be taken care of by the operating system. Alright, so let's talk a little bit about how processes can communicate with each other. So this is normally called inter-process communication. Before we actually dive into inter-process communication, we need to talk about what type of processes are there. So basically there are two types of processes. One of them is called independent processes. These are the processes that do not affect any other process, and they are not affected by any other process. And the other type of processes are called cooperating processes. So these processes, they are affected by the other processes, and they can affect other processes as well. So when we are talking about inter-process communication, normally cooperating processes, they need communication between the other cooperating processes. Independent processes, they don't care about any other processes, they don't deal with them, they are just independent. But cooperating processes, since they are cooperating with each other because of so many other reasons, and we'll talk about them, that is why it is important for these processes to communicate with each other. So, and this process of these cooperating processes communicating with each other in operating system is called inter-process communication, IPC. Now, why would the processes want to communicate with each other? Well, the first reason would be information sharing. One process wants to share some information with the other process, or one of the processes needs some information from another process. For example, one of the process of operating system would be to check if the printer is available or not. So if Microsoft Word wants to print a page, then it should get the information of the printer as well, right? So it should get some information from the operating system or from a process. It can be a cooperating process not belonging to only operating system, might be belonging to other software as well, maybe belonging to a native printer software as well. So this process of if printer is available or not might be required by Microsoft Word to print a page from that particular printer. So information sharing is one of the reasons why cooperating processes communicate with each other. The other reason why processes want to communicate with each other is the computation speed up. Now some of the programs, they are huge, they are very big. For example, Microsoft Word is a huge big program. So normally these programs are split into small modules, so that small modules, and these modules are then divided into multiple processes. As I gave you an example in the beginning of this lecture as well. So Microsoft Word is a single program that is divided into multiple processes: printing, spell checking, styling, bibliography, and so on, many others. So in order to make sure that your processes work quickly and your overall system work efficiently, and it speeds up the process of the overall system, they need to be divided into multiple modules, because as I said earlier, you do not want to, and even operating system does not allow you to load the whole program in the RAM, and because other processes need the RAM as well, and it's not the right way to go. So that's why the big process or the big program is divided into small processes that are loaded in the memory based on their need, based on the demand. So what that would do is that would help in speeding up the computation. So whenever things are required, they are loaded in the memory, and whenever they are not required, they are just loaded off the memory. So this is one of the reasons why processes would like to communicate with each other. So for example, if one of the process has terminated the communication, and at the end of that process there is a call to another process, this process will then call the other process, and that will be the communication between the process, and it will be loaded in the memory as well. Then next reason would be modularity. As I mentioned in the second point as well, large processes are divided into small modules, and those small modules are then divided into different processes. And why we do that? We don't want to fill up the memory by loading everything at once. We want to load them module by module and then process by process. So this is another reason why processes would like to communicate with each other. So one module, when it's done with it, its execution, it would like to call the other module or the other process, and that would be done through inter-process communication. And then the convenience, obviously it's convenient to load small processes in the memory instead of loading huge large processes in the memory, and then there is no space for other processes, so it's always convenient to do that. Then there are basically two ways these processes can communicate with each other. One is the shared memory, and the other one is the message passing. So let's talk a little bit about what they are. So first one, if you see this diagram, is the message passing. So if process A wants to send some message to process B, what it would do is it will send the message to the kernel. The kernel actually maintains a message queue, and then kernel sends this message to process B. So if process A, just for example, process A wants to say hello to process B, which is not useful at all, but still just to give you a very simple example, process A will send that message to kernel, and kernel is maintaining this message queue, and that message will go to message queue. Then kernel will send this message to process B. Of course, that message will have signature of the sending process and the destination process or the receiving process, and kernel will see that signature and send that message to process B. This is how message passing works in inter-process communication between the processes. The other way is the shared memory. What happens over here is, when process A wants to communicate with process B, they share a memory space. So if process A wants to share something with process B, process A will write that information in the shared memory, and process B will read that information from shared memory. Very simple way. Now these are the two ways, and we are going to go into the detail of how they work actually and why we need them. But this is the overall view of how inter-process communication works. So two ways: message passing and shared memory. Let's talk about shared memory a little bit. As I said earlier, that in order to communicate with each other, process A and process B would share memory with each other. Now what happens is, process A knows that it wants to communicate with B, so process A will use some part of its memory as the shared memory, and then it will send information to process B telling that I have a shared memory over here and I want to communicate with you, I want to share some information with you. Then process B will also try to share some of the address space of its to this shared memory. We normally call this process A is attached to the shared memory, and process B address space is also attached to the shared memory. So now when process A sends this information to process B also knows where the shared memory is, and process A and process B both are sharing this memory. Now in operating systems, what happens is, normally a space of one of the processes cannot be shared by other processes. So for example, if this shared memory space is part of process A, then process B cannot share that. Operating system does not allow that by default. Similarly, if process B has some space and process A wants to share that space, that is not possible in operating systems. So in order for process A and process B to use shared memory for inter-process communication, they need to request operating system to take off that obligation, that we cannot share our address spaces with each other. So they tell operating system that this is shared memory between A and B, and B can share this memory as well, and A can share this memory as well, and when they are sharing this memory, operating system will have no obligation. So it is important for the operating system to know that process A and process B are sharing this memory. Similarly, other processes come, they will start sharing their spaces with the processes they want to share some information with. This is how shared memory works, and this is how inter-process communication uses shared memory for the processes to communicate with each other. And this is what is written over here. Now there are some issues obviously when sharing memory, and we will talk about these issues in memory management and coming lectures as well. There are some reader-writer problems, there are some producer-consumer problems, and we'll talk about them, but I don't want to complicate this concept right now by jumping into those concepts. So this is one of the ways how processes communicate with each other. Next way is the message passing. As I just showed you over here, that kernel maintains a message queue, and process A sends the message to kernel, and kernel will send this message to process B. Now in message passing, it is very important that we have a mechanism of sharing this information some way. In shared memory, we know that we can use a shared memory, and processors know where that shared memory is, and they can get this information. So over here, in order to have message passing, in order to have communication through message passing, IPC, inter-process communication, provides two operations: send message and receive message. So it uses these two messages. So if process A wants to send message to process B, it will send message. It wants to receive the message, it will receive message. So these are simple two messages, and obviously in these messages normally they have a format. So if, for example, process A wants to send information to process B, it will contain in this message the signature of process B, and then receive will contain the signature of process A, that it is receiving this information from process C. Then this message sharing is done, and these messages which are being shared between the processes, these messages can be fixed sizes or they can be variable sizes. Fixed sizes, for example, only 4 bytes of messages can be shared, that will be fixed size. Variable messages sizing is there is no limit for message sharing, and different variable sizes can be sent. For example, one time the message size was 2 KB, and the other time the message sharing between these messages about 4 MB. So it can work with both of them. Now let's see some issues of implementation of message passing. So let's assume that process P and process Q, they want to communicate with each other. So in order for them to communicate with each other, there has to be some link between them, right? That link can be through kernel, that link can be direct, and we'll talk about both of them. So there has to be some link, there has to be some connection between P and Q, so that they can share some information with each other. And this information, as I said, that in message passing normally we use two calls, a send call and a receive call. So but there are some, before we actually implement that, there are some issues. So there are some questions that need to be answered before this message passing can actually be implemented. So first question is, how are the links established? How these links are established? Are they direct links? Are they indirect links? Is kernel involved over there? Is kernel not involved over there? So these are this is one of the very important questions over here. Then, can a link be associated with more than two processes? Now a link can be between two processes, it can be between one process, multiple processes also. So it is very important to know that link is, for example, let me draw over here to explain a little bit more about this. So there might be only one link between process 1 and process 2. There might be multiple links between process 1 and process 2 as well. So that sometimes if one of the links is busy, they can use the other link, but of course this will increase the cost. So important question over here is, can we allow single link between the two processes, or can we allow multiple links between the processes? So this is the question that needs to be answered. How many links can be there between each communicating pairs? This is again something similar. I mean, one link can be used by multiple processes, or multiple processes can use multiple links. So these two questions need to be answered. So what is the capacity of the link? How much should be the capacity of the link? Should this information be only 4 KB, 1 MB, 10 MB, 100 KB, 100 MB? How much should be the capacity of this link? This is another important question that need to be answered. Is the size of message that the link can accommodate fixed? So as I mentioned earlier, so should that size be variable? For example, if this link is only 4 KB and every time only 4 KB of information can be sent, this is a fixed one. If this link does not put any obligation on the size of the message, it can be 4 KB, 10 MB, or whatever is set. Then, is the link unidirectional or bidirectional? So in this case I have drawn all of these links as bidirectional, but this can be unidirectional as well. So only from one side the information can be sent, and the other one will always receive this information. And if that is not the case, in this case P1 and P2 both can send and receive this information. So this is also an important question to answer. Then comes the implementation at the physical level. So how physically this information should be shared, how physically this communication should be done between these processes. Uh, One of the ways is to do a shared memory again. So we share a memory space, and these processes have access to that. This is one of the ways to do it. Another one is hardware bus. We use a special hardware device that will connect these two processes, or at least a way for the operating system, a special bypass of buses where they can communicate directly. This is another way. The other one is if your systems are distributive. This is both the processes are not on the same system. We have distributed environment these days, so there are multiple. So for example, there are two computers, computer 1 and computer 2, and process 1 is on computer 1 and process 2 is on computer 2, and they want to communicate with each other. Then one way to handle them, one way to make them communicate with each other is through network. They can communicate through network as well, but that is not what we are dealing right now. We are mostly interested right now in the logical implementation of these links. So as I said, there are many questions to answer before we can actually implement inter-process communication using message passing, and these are some of the questions we need to answer. So can this communication between these two processes be direct, or can it be indirect? Should it be a synchronous one? Should it be asynchronous? Should it be automatic buffering or explicit buffering? So we need to discuss about this as well. So let's talk about that. Let's talk about direct communication first of all. So processes can directly communicate with each other. They can use message passing like this. So they can use calls like send P message, assuming that P is trying to send message to Q. So this would mean that this message will be sent to P. So where do you want to send this message, and what is the message? So it will take two parameters. And receive the message is similarly, this is from where to receive this message and what is the message. So these are two directives that we can use in message passing in direct communication. Then again, there are some properties of our communication link in direct communication. What we do over here is since it's a direct communication, there is no kernel involved. These two can talk to each other directly. So in that case, what would link do? I mean, what would be the properties of the link? So links are normally established automatically. So they don't have to, processes don't have to create a link. Just like what is happening in message passing, if you see, processes have to initiate the shared memory. So process A will share a memory, then it will communicate with B using operating system. But over here, if you see in message passing, it's important that this is done automatically because it's a direct communication, and this overhead should not be done by the processes, because if all the processes will start sending messages to each other, then it will be a chaos. So this link will be automatically created, and then link will be associated with exactly one pair of communicating processes. So this is one of the link, and this will be associated with one pair only. So if we have other processes also like this, if we have other processes as well, this link will not be associated with those. This will not be associated with those. So link will be associated with only one communicating process. So it will be associated with only process A and process B. This link will not be used between process, for example, process 3 and process 4. It will not be used between process 2 and process 3 and process 4, for example, right? So between each pair there exists exactly one link. So it's pretty clear that between each process there is going to be only one link. There cannot be multiple links. So this is another property. The link may be unidirectional, but it can be unidirectional, but normally it is bidirectional, and it does make sense because we are saying that there is going to be one link between the two processes. So if we have unidirectional, then we need to have two links between it. So these are the properties when we are talking about direct communication in message passing using inter-process communication. Now if we talk about indirect communication uses mailboxes. So what they do normally is they normally have a mailbox in the middle, and that mailbox is used to share the information, just like what we did for shared memory. So there is this is the mailbox. This mailbox will contain all the information, all the messages, and processes will take this information from the mailbox. So if process A, P1 wants to send information to process B, process A will send this information to mailbox, and process B will collect this information from the mailbox. This is how they will communicate. So they will not directly communicate with each other, they will communicate through the mailboxes. Now if we talk about the properties of the communication link established only if the processes share a mailbox. So this link will be established between process A and process B only if they share a mailbox. So if P1 knows there is a mailbox that it shares, and P2 has a mailbox as well, which happens to be the mailbox of P1 as well, then this link between P1 and P2 will be created, which is this link, indirect link, P1 to mailbox and then from mailbox to P2. This link will be created, otherwise this link will not be created. A link may be associated with many processes. In this case, this link may be associated with many processes. So this link might be coming from here, P3 to mailbox as well, which is absolutely fine. Then each pair of processes may share several communication links, and there can be several communication links. So they not necessarily have to be one link. It can be another link from here. It can be multiple links because there can be multiple mailboxes as well. And link may be unidirectional or bidirectional. As I said earlier, it can be unidirectional, it can be bidirectional. Now some important operations over here is whenever a message passing using internet communication is done, there needs to be a mailbox that has to be created. Once the mailbox is created, then the message passing is done, and then that mailbox is destroyed. This mailbox needs not to be there forever, and it doesn't make sense keeping this mailbox if it is going to be empty for the rest of the time. So it's a good idea to remove that mailbox. And how to use the mailbox: send message A, send a message to mailbox A. So this system call will send a message to mailbox A and receive a message. It will receive the message from mailbox A. It's a very simple. Let's talk about one more issue, and I think this is the last issue we want to talk about, and then I will quickly go through buffering and synchronous and asynchronous. But for indirect communication, this is the last issue. Let's assume that we have three processes: process 1, process 2 and process 3, and they are sharing a mailbox A. So we have something like this, and they are sharing the mailbox. They are all sharing the mailbox. Process A sends a process. So process A sends a message in the mailbox, and process 2, let me put these the other way around to make it more understandable. So process A sends this information, process 2 and 3, they both receive this information from the mailbox. So process 1 is sender, process 2 and process 3, they are receivers. So an important thing to note over here is, okay, the message is over here. Now they both are listening to mailbox, right? Now this message from P1, who will receive this message? P2 will receive this message, or P3 will receive this message? One way is to put a signature. Who is this message for? Which is what modern operating systems are doing. But it is important that in that case also P2 and P3, they periodically check the mailbox. If there is a mailbox and it has a signature P2 and P2 never checks the mailbox, it doesn't make sense, right? So it is important that periodically P2 and P3, they check the mailbox. But going back to the old system, that it is important to know that who receives the message. In order to fix this issue of who receives this message, in case there is no signature available, then what we do is we allow a link to be associated with at most 2 processes. So there will be a link. So there is one link P1, and that link is P1 to mailbox and mailbox to P2, and there is a link P1 to mailbox and mailbox to P3. Now we allow only at most, we allow a link to be associated with at most 2 processes. At most 2 processes. Two processes mean P1 and P2. So there is a link which is between P1 and P2, and there will be no link between P1 and P3 through mailbox. In this way only P2 will be able to receive this information. One way to solve this problem is of who will receive this message is just to have a link that is between 2 processes. And in this case, since P3 is not linked with mailbox, P3 will not receive anything, P2 will receive this message. The other one is only allow one process to execute the receive operation. So if the link is not the way we want to solve it, so if there are 2 links between process 1 and process 2 and process 3, so there is a link between process 1 and process 2, there is a link between process 1 and process 3, so we are in the same situation as before. Now in this case, if we have something like this, the other solution is only make one of the process to receive the information. So don't allow other process to receive the information. This is another important thing. This is another important thing to note. So in this case, when only one process will be allowed to receive the mailbox, then only that process will receive that information, and this will obviously solve that problem as well. And last one is to allow system to select randomly. So operating system will randomly select which process will receive this information, and that message will be sent to that process as well. Our modern operating system, they do have signatures for the processes, so mailbox can send that information from the for the specific processes as well. So in that case, there is not much of a problem when it comes to indirect communication. Now the last thing is message passing through synchronization, and I will quickly go through this. It says it actually has just like direct and indirect communication, is just to smoothen the link properties of indirect communication. So the message passing can be blocking and can be non-blocking, and it's a very simple concept. So if message passing is blocking means synchronous. It means that blocking send, which means that in that case sender is blocked until the message is received, right? So synchronous means that the sender will be blocked until the message sent by the sender is received by the receiver. Similarly, blocking receive will do the same thing. The receiver will be blocked until the message is available, so they will not keep on going and checking the mailboxes. So this will smoothen up the synchronization between message passing. The other one is asynchronous. In asynchronous, the message will be sent by the sender and it will continue its stuff. It will keep sending more messages. And non-blocking receive will keep on receiving messages. It might be a null message. It will keep on checking the mailbox, and mailbox might not have any message for it. So different combinations are available. Different combinations are available to smoothen the message passing between two different processes. And lastly, we have buffering. Buffering is again, it has three ways of providing information using message passing between the processes. One is the zero capacity queue. It means that there is no queue at all, so the communication will be direct between sender and receiver. We are talking about mailbox in this case. So communication between sender and receiver will be direct through the mailbox, but mailboxes will not be saved in the mailbox because there is no queue, and they have to be mailbox has to directly send that information to the receiver. Then bounded capacity. It means that some messages can be saved in the queue, but if queue is full, then sender will not be able to send more messages. Then we have unbounded capacity, which is infinite length. The sender will never wait. It will keep on sending the information, and receiver will receive the information whenever they are available. So these are very simple concepts which I wanted to quickly go through. We are not going to code this message passing today because I think most of these concepts will be covered in the coming exercises which we are going to do for process communication and thread communication. So we will cover that over there. But for today's exercise, what we're gonna do is we are going to talk about how to create a process, parent-child processes, how to distinguish between them. These are the exercises we are going to do today. So this is it for the theoretical part. I know it's a lot of information, but I just wanted to make it clear. It's only, I think, how many, 37 slides. Slides are not too many. I could have gone very quickly through all these slides, but I wanted you guys to understand what is the concept behind all these things. So it is very, very important for you to understand what is going on. I know your seniors might have scared you a lot that this is a very, very difficult course. I know it's not an easy course, but I do believe that if you understand the concepts properly, this is not a difficult course at all. So you understand the concepts and we implement them, you see what is going on, why these concepts are used, how we use them for implementation. It's going to be a piece of cake for you, but you have to do it together with me, and I will try to make it as simple as possible for you. And as always, if you have any questions, let's meet, let's discuss, and let's remove any confusion in your mind you have about any concept, and it's gonna be fine, hopefully. Alright guys, thank you very much. I'll meet you in the other video. I'll stop this theoretical part over here. Thank you very much. Have a nice day.